I'm Jonathan Harlap. I'm Director of Technology at Wattpad. And the obvious first question is, what is Wattpad? So Wattpad is what's going to be the origin of the next blockbusters and bestsellers and binge-worthy TV series that you end up watching. We've been transforming how people are reading and writing, how people get published, how movie studios find new voices. And over the last few years, we've been leveraging our community of storytellers, our data, and our insights to drive movie studios to reconsider how they are sourcing stories. Our flagship app, called Wattpad, has 65 million people coming every month, spending 22 billion minutes every month connecting around 500 million stories in over 50 languages. So it doesn't sound like we're a startup, but we also are still iterating and pivoting continuously, and that's not our only product. We also have Tap by Wattpad, which is interactive fiction, chat style with multimedia. We also have Wattpad Studios, which is a new arm that is working with global entertainment partners to drive that change in film and TV and traditional publishing. So that said, we're multi-armed. The flagship product is very large at this point, and a few years ago, we reached that scale moment when we needed to make that change from the monolith to microservices, and I'm sure many people here have either done that or are thinking about doing that. First off, if you're thinking about doing it, don't. If you need to do it, you know you need to do it. It's because your org size has grown, your team group has grown, and so forth. If you're thinking about doing it just for like technical reasons, odds are it's not the solution you're looking for. But that said, if you do go down that road, there are some architectural choices that you'll have to make. And the first one that we considered when we went down this road about 4-ish years ago was whether to use an orchestration or choreography architecture as the primary pattern for these microservices. So I'm going to talk a bit about what orchestration and choreography are. I'm going to give you a little bit of info about what some characteristics are of the message bus that's going to be the underlying fabric for choreography, and the message processing approach that you can take if you're going to go down this road. And then I'll tell you about what our actual experience has been now that we've been doing choreography for a few years. So, orchestration or choreography. Orchestration is the thing that you probably know and might not even have a name for. It's a client request comes in to the entry point of your world, maybe an API gateway. That then makes requests to a whole bunch of internal services. It aggregates data from all those results and turns it into a single result for your client. In our world, if we take Wattpad app, we have stories and users and comments because we're a social network around stories, so people are able to comment on stories. So that means that if I want to give you a list of stories, I might make a request. It might then hit the stories service to get metadata about all the stories that were in this recommended list. It might then hit the user service to get usernames and avatars for all the authors of these stories, and it might hit the comment service to get the social proof for each of those stories of how many comments does this story have. It's really, really easy to design and build with orchestration. The downside is that you have a lot of points of failure. So when one request comes in, it depends on all of these back-end systems being up to be able to service that one request. And the other downside is that it does result in an internal request explosion where one incoming request from a client can turn into dozens of internal requests. So the amount of traffic happening within your clusters is very large. That said, it is very easy, so that's a big advantage. Choreography takes a different approach. With choreography, every service is able to respond to queries independently of all the other services. You end up with an eventually consistent read model across your whole world. So when a write request comes in, it goes possibly through the API gateway still. I've dropped that from the slide, but it might still be part of your world for auth reasons or things like that. But it gets to one service that is the source of authority for that type of content. And that service will update its local database and do whatever it needs to do, but then it will emit an event onto your messaging fabric that other services can subscribe to and consume. And when they get those messages and process them, they'll update their local databases. So a change to comment count will be only writing in the comments data store initially, but it would then potentially emit, either immediately or eventually, a message saying, hey, the comment count for this story has gone up. The story service might subscribe to that and update its store so that when a read comes in for that story list that I mentioned before, it only needs to do a local query against its database, and it has an eventually consistent comment count available to it immediately. Here's what comments look like, and I just want to kind of reemphasize that like comments have usernames and avatars, not just bodies and timestamps. And so if you consider the frequency with which users change their avatar or change their username on our platform, that can happen pretty often. So consuming the comments view can result in a huge explosion of requests with orchestration. If I retrieve a page of comments and it's got 50 comments on it, and I need to hit the user service for every user's username and avatar, because I only stored an ID locally in the comment service, that would be up to 50 more requests just to service the one comment list request. And to give you a sense of what scale looks like and the unevenness of our content, some unpopular stories will have 0-ish comments, and some popular stories can have literally millions of comments on one story. So it's a very, very uneven thing. So, a very simplified view of our world, just a piece of it. We have users, we have stories, we have comments. Users can update their usernames, their avatars. Story lists and story views care about that to be able to show the author info. Comment views and lists care about that to be able to show the author of each comment. Stories care about comments because they want to show social proof in terms of number of comments. And so you can imagine with just this trivially simple model, the internal request explosion I was talking about can get very quickly into hundreds of thousands of internal requests for every external request that lands on the story or comment service. And so when we were looking at this general problem space, this didn't feel like the right design. The idea that everything was coupled tightly, that every individual service's availability was going to dictate the aggregate availability, it just didn't feel like the right approach to go with microservices. So, let's say we want to go with choreography. Step one, how do we do messaging? And there's a key mindset around messaging, which is when you're talking about like an RPC style API, I'll call it naive, but I don't mean that as a diss, it's beautiful. There is something very simple about it. You get a request, you respond. If it didn't work, you respond with a failure. Everything is clear. When you're doing asynchronous messaging, you suddenly have a very complicated world. You get a request, you emit a message, you give a response now, and processing of that message will happen later, if ever. And so you have to be able to give some guarantees around what's going to actually happen in your application. So there's two characteristics that I'm going to say you really have to focus on when choosing your message bus technology. And I say message bus, and it sounds like I'm going back to the 90s, but the concepts are the same because everything's really cyclical in our world. So the two are delivery semantics and ordering. Delivery semantics basically means when I send a message on this queue or on this bus, will I have at least one copy of that message received on the other side? Will I have at most one copy or exactly one? We are using SQS very heavily and SNS as well. And so we looked at this and we said we want at least once messaging. If we get something duplicate times, that's okay. We just never want to lose things. And with at most once, I mean, I like to compare it to dev null. I will send messages to dev null until I'm blue in the face, and I guarantee you get at most one copy of each of those messages. Exactly once is a bit of a magical rainbow. SQS, FIFO, Kinesis, there are more products that will talk about exactly once message delivery. There's a caveat that you have to keep in mind with all of those, and it's that that's true when there are no errors, but as soon as you have processing errors in your application, suddenly you have to ask what's going to happen to this message. Will it stay on the queue and I pick it up again later? Now I have duplicate delivery. Do I have multiple consumers acting concurrently? Now I have out of order processing and so on. So I tend to suggest that even if you think you have exactly once capabilities, you still design for at least once. The other one I mentioned is ordering. So you can have strict ordering. The first thing I put in will be the first thing that comes out. In reality, it's not global like that. It's kind of per partition or something of this nature. You get to control what dimension is in order. But things like Kinesis streams and SQS FIFO will give you strict ordering, and it does make life a lot easier. If you use SQS standard like we have, then you have no ordering guarantees. You will get things in scrambled order. It's approximately in order, like something sent an hour ago will have arrived before something sent now. But within the microseconds or milliseconds that our world is operating in, there is no ordering guarantees. So once you've sent messages and you know how they're going to be received, you have to start planning for how are you going to process these things. And effectively what you're saying is I've got some new event, some new piece of data, and I want, as a consumer, to incorporate that new information into my local understanding of the universe. So I'm going to merge that new message into my local state. So there are 3 properties of merge functions. This is not something to like obsess over. It's more just I want to give you the language because we're going to use it. Associative processing means that you can, given 3 messages, you can process A and B together and then merge C into that, or you can process B and C together and then merge A into that, and the final result will be the same. Commutative means that you can get them out of order, and idempotent means that if you process the same message twice, you get the same result. Immediately just want to make sure we understand the words associative, commutative, and idempotent, because depending on the characteristics of your message bus, you have to have certain processing requirements. So if you're going to get out-of-order messages, like SQS standard, you have to be able to do commutative processing. If you have at most once, then you have to be able to recover messages, and for sure you can't. If you have at least once, you have to have idempotent because of dupes. And if you have distributed consumers, which means that things are going to get processed in bunches on one and different bunches on the other, and then combined, then you need to have both associative and commutative. So there's this thing, and it's like got really big in academia, and that some of it leaked out into like the real world, and it's conflictly replicated data types, or CRDTs. I'm not going to bore you to death with like tons of details about it. I just want you to know that like this language exists, and it's a language for discussing and thinking about merge functions and data types that are going to be processed in a distributed fashion. And the key about it is that you'll see state-based or convergent CRDTs, and you'll see operation-based or commutative CRDTs. Only the first one gives you idempotency, which means for our use case, only the first one is appropriate. Don't worry about the rest. For a CRDT, and when I say that, I'm going to mean state-based, there's basically 3 functions you have to worry about. How do you query a value out of your local view of the universe? How do you update your local view of the universe because someone has sent you a write? And in that moment, you also send an emit out to other members of your cluster. And how do you merge the updates you're receiving from other things? And to give a sense that like all of this, complicated sounding academia, the max function, the greater of 2 numbers, is an example merge function that satisfies a lot of these criteria for a lot of types of CRDTs. I'm not going to get into, but I'm going to leave in the slides, so a brief moment. If you're watching later, pause. And you can also have more advanced types for counters. You can see it's slightly more advanced, but you can also see it's still a very simple bit of pseudocode. The key is we had to make these decisions about how are we going to build our architecture. We looked at these options, and we decided that we thought it would be fun to do choreography. And I say that because while it is true that we saw a lot of advantages in choreography, it's also true that a major factor we had in our dev team at the time was this one sounds a lot more interesting and exciting for us as engineers than the other, so let's try that out. Part of what I'm going to say is, don't do that. We took the approach of state-based as a default mode. Last writer wins register is the name of the CRDT if you want to go look it up, but we don't have to worry about it. And the key is that whenever a service has a write locally, it emits an event to SNS, to a topic, and the naming convention of those topics is how things know how to integrate. And anyone who writes a service that cares about the events coming off of another service or another data type will create its own SQS standard queue, will subscribe to that topic, and will get those updates. And because we are a predominantly, for our microservice world, Go shop, we have a framework for writing SQS consumers in Go that means that you don't need to worry about writing whatever code there is around message management, just the message processing function itself, and then the framework lets you make quick and easy SQS consumer programs. So that has made it possible for us to write a whole bunch of these very, very quickly. The other thing of note is that when I talk about the different members in a distributed system, the different nodes that share data, in this architectural level, each service is itself a node in a distributed system, right? So the story service is effectively an actor in this distributed architecture. Within each of those services, there may also be internally a cluster of distributed nodes that need to share information. The same language and the same patterns apply there as well, and that is one of the nice things about this approach is it works very nice from a fractal mindset of what works at the outermost architectural scale also works at the innermost single service scale. SNS and SQS standard, as I said, is the basis of this whole world, and one of the things is it's not just that we chose that because at that moment in time that was the state of the art on SQS, on AWS. Even since then, we've had times we've reevaluated. Should we change to Kinesis? Should we change to SQS FIFO? Should we change to other products entirely? And we kept coming back to SQS just worked, and at this point we can create a queue and it can be processing hundreds of thousands of requests a second, messages a second, and it's never a topic of discussion amongst our teams. It's never something that pages our on-call teams. It's just boring, simple, beautifully working software. And so that, as a messaging fabric, makes it ideal. It's the last thing you want to worry about. I said at the beginning that there are some reasons not to go down this road. There are certainly dragons on this map. The first and foremost is complexity. I've explained that there is some mathematical formality that makes this work, but as an engineer entering our work environment, you have to wrap your head around all of this and how this works and why it works before you can start being a productive contributor. That complexity is expensive. So reason one, if you don't need this, don't do this. Another one is duplication. Every of these services ends up having a partial replica of the database owned by other services. The comments service has a partial replica of the user's database. The stories service has a partial replica of both comments and users' databases, and so on and so on. And this replication, storage is cheap, so like it's not a big deal, but it does mean that you have this consistency problem that can crop up, and it does mean that you have this maintenance problem that can crop up. It is more to maintain. So that is a challenge. The network bandwidth one is one that people tend to come up with, that like you're sending these big furry state objects instead of just requesting the single values of an object that you care about. That one's actually not a dragon. That one's a bit of a lie, because you send a state update once when it occurs, you consume it once when you care about it, and instead you do that instead of making 100 requests to satisfy one external request. And so on aggregate, you end up spending less bandwidth now, but you do send bigger objects, and this raises a red flag for everyone when they first start looking at it. The other one that is definitely a dragon, if you do not take this into account when doing UI design, is eventual consistency can lead to UI inconsistency. If I show you a list of story, if I show you a story next to it, the comments for that story, you will see the author at the top of the story. You will see the author again, because they will likely be an active commenter responding to other people's comments. Those two services have their own local version of someone's username and avatar. And if I've just changed my avatar and you see it two different versions on the same page, that will be a jarring experience. And so you have to keep this in mind when designing your UI and how your application interacts on the client side with this back-end architecture. So, in short, choreography is hard. It does work very well when you make the effort to do it well. It took us a long time to figure out where the icks are, and that learning experience, I don't know how much of it would really transfer to others, because a lot of it is specific to how we write our microservices, how we operate our infrastructure, you know, the modules we've built in Terraform to allow us to create all these things. You have now the knowledge that there exists a thing called CRDTs, and you can Google them and read. There's a brilliant paper from INRIA that has a whole catalog of CRDTs. So you don't need to like invent these things. Someone has done the inventing work. There's libraries out there for most languages, so like you might not even need to implement it. But the biggest lesson is do the simplest thing that works for you. And for us, this was not the simplest thing, and we're still paying for it now. Our system works, our site stays up, stories can go down and comments can keep working, and that is a beautiful experience. But it's hard to say if that was really worth it. But that said, distributed systems are hard. Microservices are hard. The amount of tooling you have to create if you go down this road is substantial. So if you are a small startup and you are still early and still figuring out what your product is, as many of us are, including Wattpad with TAP, is definitely still figuring out what our product is. This architecture does not work well for that because it locks you into a certain amount of rigidity early on that you don't want to have. So adopt it when you get to that level of scale that this will solve your problem. But that's the real lesson. And if anyone has like detailed questions after this, like super specific, just grab me. I'm happy to talk your ear off. I love this stuff. And that's it for me. So thank you all.
Jonathan, thank you very much. Fantastic. We do have time for maybe one quick question if someone has a question for Jonathan.
So are all of your microservices kind of like a read replica? Like, does every microservice have a portion of the database? Can a client go to any service to get, like, could you go to the comment service to get stories, for example?
So there are a few special exceptions that actually follow orchestration for very good reasons, like the home experience that gives you a bunch of recommendations of stuff in a whole bunch of modules. That one actually uses orchestration. But all of the services that follow the choreography pattern, they have their own database. We strongly prefer DynamoDB for them for cost and flexibility reasons. And yeah, they have a partial replica of other databases, only the ones that they care about and only the columns they care about, and sometimes transformations of the values they got in. So like the story service might only maintain the count of comments, not the actual comments, as an example.